Hi everyone. Today we are starting our mini series on centripetal force. This will be centripetal part one. We'll have three parts to this section of chapter 6. So we'll start with centripetal force. In a hydrogen atom, the electron orbiting a proton is subject to an attractive force of 8.20 times 10 to the negative 8 newtons. If the radius of the orbit is 53 picometers, what is the frequency of orbits in revolutions per second if the mass of an electron is 9.11 times 10 to the negative 31st kilograms? Draw it first. So what we will do is we will draw it first. So we have our proton, right? And we have our electron. It is going around in a circle. And it has this attractive force on it. Now, what we're going to look at here is the frequency of orbits in revolutions per second. So what does that really mean? So we have some information on centripetal force. Let's first narrow down what is centripetal force and what would we use it? How could we use it to solve for frequency of orbits in revolutions per second? So we have first F equals ma, right? But we also have, so we're dealing in circular world where we've got centripetal acceleration. Centripetal acceleration can be omega squared r, or it can be v squared divided by r. So if we turn this force into centripetal force, that gives us two different equations. We have m by square r divided by r. And we can use either one of those for centripetal force, just depending on what better suits our scenario. So we also know some of this information already, right? The centripetal force is 8.20 times 10 to the negative 8 newtons. Radius is 53 picometers, right? Radius right there. Pico is 10 to the negative 12, so we can say that is 53 times 10 to the negative 12 meters. And last, we have the mass of the electron. This is a fundamental constant in physics that if you continue physics, you will run into it quite often, but that's 911 times 10 to the negative 31st kilograms. So we have all of this information. Where in all of this could we get the frequency of orbits in revolutions per second? Well, omega can be in revolutions per second. Velocity can as well, and we'll talk about that. But for now, we will work with our omega, our m omega squared r. So we have Fc equals m omega squared r. If we want to solve for omega, we could take Fc, divide by mass and radius, take the square root, and you would get omega. So if we do that, this is going to be a lot of numbers, so heads up. We have square root of 8.2 times 10 to the negative 8 divided by mass, which is 911 times 10 to the negative 31st, right? And that is times the radius, which is 53 times 10 to the negative 12. Divide that, put it all under square root, and that is what we'll get for our omega. 4.121 times 10 to the 16. So that is 4.121 times 10 to the 16th. And what unit does that naturally have? So naturally, omega is going to give us radians per second. but we need revolutions per second, right? So let's move on down here. If we take 4.121 radians per second, how can we convert radians into revolutions? Well, 2 pi radians is the circumference of a circle, right? Which would be 1 revolution. So if we divide that number by 2 pi, we would get 6.56 times 10 to the 15. 6.56 times 10 to the 15. Moves darn fast. It's moving at almost 6.5 quadrillion revolutions every second around this hydrogen atom. I guess around the proton in the hydrogen atom, right? So you could also do this by using your mv squared over r if you would prefer. What you would do is you would solve for v with mv squared over r, which would give you meters per second. But then to get from meters to revolutions, right, you need to know how many meters are in one revolution, which would be the circumference, right? We don't know the circumference of this, but we do know the radius. And circumference in terms of radius is 2 pi r. So you would take the meters, divide that meters per second, divide it by 2 pi r to get your revolutions per second. And then you would be able to do the same thing, and you should get the same answer as well. Okay. So that is how we could find the omega, the revolutions per second, for an electron in a hydrogen atom. Now we have a conical pendulum. Okay. Conical pendulum is a pendulum that moves in a circle, as you can see. Instead of just moving back and forth, it moves in a circle. It's called a conical pendulum because if you watch the path that the string takes, it would form a cone, right? So what is the force causing the pendulum bob to remain in the circle? Well, if we look over here, right, we have these thetas, right? So here, okay, so there is another theta there. There is our theta up top as well. So we can use this as our free body diagram right here. That can substitute as our free body diagram. So our tension, right, has a y and an x component. Mg just has a y component. So let's talk about what it means when it asks remain in the circle, right? What is causing the pendulum bob to remain in the circle? Well, objects will naturally, just moving through space, travel in a straight line, unless there is some surface or some force that's going to cause it to change direction. It just wants to go in a straight line. So what's causing it to remain in the circle would be the string, right? The string has this inward force right here along the radius. And that would be T, a component of T, that would be sine theta, right? If we look at our theta up here, if you look at the theta on our T, it would be opposite of that theta. So T sine theta is actually our centripetal force. Now remember, centripetal force is a force that's pointing towards the center of a circle, just the same as acceleration. Centripetal acceleration, also called radial acceleration, is just the acceleration along the radius in circular motion. Centripetal force is the force along the radius in circular motion. So T sine theta is our centripetal force. Now, if we assume the string is massless, we want to derive an expression to find the speed of this mass in terms of L, G, and theta. So we can start by writing down what we know, right? Let's zoom down here. Okay, so we know that, well, we've got Fc equals T sine theta. Fc also, it asks for speed, right? So we're going to use V, mv squared over r. What else do we know? We know that, actually, no, let's just leave it at that, and then we'll go from there, right? So Fc is mv squared over r, which equals T sine theta, right? There is nothing else in the x direction. So we've got F equals ma, F is T sine theta. So let's solve for V. V would equal, let's multiply the r over. So we have T sine theta times r divided by that mass, all under a square root. But it only wants theta, which we have, g, which we don't have, and L, the length of the string, which again, we don't have. So to get rid of these units that we don't want, which would be R, tension, and mass, we need to solve for them and substitute them into the equation. So let's solve for tension first. That's the easiest one to do. If we look at the summation of forces in the y, right, we have T, what would that be? T cosine theta minus mg would all equal 0. So that means T cosine theta equals mg. It's got to balance because there's no acceleration in the y direction, right? It's just in the x direction. So if we want to substitute out T, we would have T equals mg divided by cosine theta. So let's substitute that real quick. We have mg over cosine theta times sine theta r over m, all under a square root. Okay, so the m's will cancel there. Sine and cosine can become tangent. So then we have the square root of g tangent theta r. And I'm keeping r on the outside because we want to get rid of it, right? So we have g, that's legal. We have theta, legal, but r, that's not a legal variable for this problem. We need to get that in terms of L. So if we look over here and we get rid of some of these drawings, we can actually look at L in terms of R, right? So here we have R. Here we have L. So what is R in terms of L? Well, if we look here, if we take L sine theta, we would get R. We would get that length R. So we can actually put in L sine theta for R. Let's do that. So we have the square root of G tangent theta times L sine theta, all under a square root. And that would be our answer. Not the prettiest answer we could get, but it is in terms of G, L, and theta, just like was asked. So that's how we can do that. Now that's going to be common. It's going to ask, in physics, it's common to ask to derive an expression in terms of specific variables. And when you need to get rid of those variables, think about the ones you can get rid of easiest. And tension is always number one on that list. It's easy to get rid of tension and substitute that out in most cases. You don't want to try to solve for mass. Mass will usually cancel out somewhere in your math. So don't go, if you can't use mass, like in this scenario here, where we have T, R, and M, don't try to solve for mass. Mass will usually cancel out when you start solving for other things. So that's how we do that problem. Next, we have banked curves. Now, why do civil engineers bank the curves of roads and racetracks, like a velodrome and a luge run? So if you guys haven't seen a velodrome, Google that one. Velodromes are basically a curved racetrack. But if we look up top, right? This is a turn with no bank, right? And the only thing that's causing you to turn is the static friction of your tires. As long as you're not drifting around this corner, it's static friction that is causing your tires to roll, and it's causing you to turn and causing you to take that turn. Now, if you bank it, though, we are banked some angle theta down here. We have the force of gravity, but over here, the normal force is all of a sudden at an angle. And the normal force, okay, there is a normal in the x and a normal, and a normal in the y. So that is going to actually cause the normal force to help you make your turn, and you don't have to use as much of that static friction in your tires, so you don't actually have to turn the wheel as much. So here we just have normal force causing that turn. So that's why we bank roads. Very common in highways to bank roads to make a turn easier for the driver. Now, derive an equation for the bank angle needed for an object to undergo circular motion at a given speed v in the absence of friction. So we're basically going to recreate the free body diagram we have over to the right. Okay, so we have R, and then we have a normal force, right? Normal force coming up at some angle, right? And we will say that that is an angle relative to the vertical. So that is our normal force. And then we also have our gravity, our mg. And there's no friction, so there's nothing left, right? So here we have normal force in the x. Here we have normal force in the y. And the only centripetal force that we have going for us is the x component of normal force, right? So Fc, it's a funny little F there. So we have Fc would equal normal force in the x. Now, that means that normal force must equal MAC, right? That's the equation for centripetal force. So what do we want to use? Do we want to use V or omega? So if we look back here, it does say given speed V. So we will use mv squared over r. So we have nx equals mv squared divided by the radius of the turn, right? And we want to find an equation for the bank angle. It didn't give us any required variables, so we kind of have free reign there. But what is n? What is our normal force? Well, our normal force isn't just mg anymore, right? So if we need n in the x direction, let's solve for n in the y direction and substitute that in. So we have summation of forces in the y equals ny minus mg equals 0. So ny equals mg. And ny, if we look at our free body diagram, that's adjacent to our angle. So that would mean that we can say n cosine theta equals mg. Therefore, n equals mg divided by cosine theta. Now, if we plug that in, nx must be n sine theta. But if we plug in our n, we have mg over cosine theta times sine theta. You can already see that there's a tangent forming there. So we have mg tangent theta for nx, right? So if we plug that in, take this and put it here, we can say that mv squared over r equals mg tangent theta. M's will cancel pretty quickly. So then if we solve for theta, okay, we have v squared g divided by r equals tangent theta. I'm sorry, that g shouldn't be there. That g goes down on bottom. V squared over gr divided over. So theta equals the tangent inverse of the speed you need to go squared divided by g and the radius of the turn. So this can be applied to whatever circular path we want to take if we want to neglect friction. And neglecting friction would just make the turn easier on us. Now, if you're going a certain speed v, then you can plug that in, and then you need the radius of your turn, and you can find the bank angle needed to undergo circular motion at any speed v without friction. Now, our last problem for this video. Bank the track for the Tigers. So, Mr. Pentecost wants a circular track of 20 meters to be built with a bank angle theta to allow runners to go for a 4-minute mile. Now, what value would you use for theta, and is this reasonable? Now we're doing a circular track, so it is not the track pictured there. That is the, I believe, University of Houston indoor track. But you can see there that on indoor running tracks, you actually have a banked curve as you go around there. That is to save space along the in the gym, right? So that you don't have to build a full-size track. If you bank it, you can actually build a shorter track. So what would you use to find your value theta? And then we'll answer the question, is this actually a reasonable value? So let's look at this. We know this from last time, right? We have, let's write our givens first. We have the radius is 20 meters. We are solving for angle theta. And we want to allow runners to go for a 4-minute mile. So that means it takes them 4 minutes to run 1 mile. And that would be their velocity. So that's going to be a weird conversion, right? Let's convert that real quick to meters per second. So we can actually invert that, right? That also means that they're going to go 1 mile in 4 minutes. Means they would run a 1/4 mile per minute, right? So you could say 1/4 mile per minute, right? That's not breaking any rules there. So if we take that times in a line, 1 mile is, we will say that is 1609 meters per mile. Then we have 1 minute is 60 seconds. So then we will end up with meters per second here. So we take 1609 divided by 4 divided by 60. You get 6.7 meters per second. Okay, so we will use that for our velocity. Now, we want to know the angle. Well, we just got an equation last time, right? We're going to neglect friction. Here we don't know the friction values. So we have theta equals the tangent inverse of v squared over gr. So let's assume we got theta equals the tangent inverse of v squared over gr. That would give us the tangent inverse. What is our v? 7 was that divided by 9.81. And our radius is 20 meters. There you get 12.89 degrees. 12.89 degrees, so about 13 degrees to run that 4-minute mile on a 20-meter radius track. Now, that seems kind of steep to run on. So we actually have some more information. The average indoor track is recommended to have a 10-degree bank. So that is actually a little too steep, and it could be difficult to stand on. It can also lead to injury if you're running on it for too long. So 13 degrees is a little excessive. But let's move on to number 2. I don't know that I would call that reasonable, but so the coefficient of static friction for rubber on rubber is approximately 1.16. So that would be similar to rubber shoes on rubber track. What is the angle of repose for rubber shoes on a rubber track? And could you stand on the new banked track without slipping? So if you guys remember, the angle of repose, we calculated that last chapter, is the tangent inverse of the static friction coefficient. So if we take the tangent inverse of 1.16, we get a massive number of 49 degrees for our angle of repose. So the rubber shoes would be able to withstand the rubber track, right? They are made to grip each other, but that doesn't mean that it's going to be comfortable, right? But it would be doable, right? It's only 3 degrees more than a standard incline track, so not too big of a deal if we wanted to do that. All right. That is it for Centripetal Forces Part 1. We will have 3 videos in this series, like I mentioned before, and then we'll continue on through Chapter 6.